Hello and very good evening to you all. I am Shambhasubra Ghosh, HOD of Electrical Engineering Department of IMPS College of Engineering and Technology, Malda, West Bengal, India. I am also the coordinator of this webinar session. I welcome you all in today's webinar on the art and challenges in designing printed antenna arrays. Here I want to take the opportunity to welcome our today's honorable speaker, Dr. Abdul Latif Slimani from Sidi Mohammed bin Abdullah University, Faculty of Sciences and Technology, Fez, Morocco. Sir, we are very thankful to you as you have accepted our invitation to present this webinar. We will shortly start our presentation. But before going to start this session, I would like to mention the guidelines to be followed by the participants during the webinar. Please kindly mute your microphone to ensure that there is no background noise during the webinar. Also, never click on the present now option during this session, as this present now option is only for the honorable speaker. In case you accidentally exit from the meeting, again click the meeting link and click the rejoin button to join the session. Please never mute our honorable speaker. I repeat, please never mute our honorable speaker. And don't type anything unnecessarily in the chat box like good evening, participant's name, etc. This chat box you can use at the end of the presentation during the question answer session to raise your questions or queries. At the end of the session, we'll share the feedback form in the chat box. Please do not forget to fill up the same for the successful generation of the e-certificate, which you will receive in your email ID provided within the 14 working days. Now, I would like to request our respected principal sir to say a few words. After that, we will start today's session. Over, thank you, and over to you, principal sir.
Thank you very much, Professor Ghosh. First of all, I would like to thank you each and every participants who have managed their time for attending the today's webinar session. And obviously, I wholeheartedly welcome our respected honorable speaker for today's session. But before starting the session, I would like to share a few things that I would like to introduce myself. Dr. Sudipto Das. I'm the principal of IMPS College of Engineering and Technology. And on behalf of my college, I am welcoming you all to the session number 11 of our webinar series 2020 that is conducted by IMPS College of Engineering and Technology, West Bengal, India. And likewise, our previous webinars, we are targeting the key topics or key points each and every day while we are trying to conduct the webinars. And for the RF and microwave community or the researchers, professors, UG, PG or PhD students, so for them, we know that for the antenna community or particularly for the communication systems, what is the vital role of an antenna? And apart from nominal single element antennas, as an antenna designer or as an antenna engineer, we always focus to design the antenna array or array antenna, particularly when we require higher number of gains. But other than only gain, there are lots of other concerns. And that's why I have selected this topic today. And the topic is really interesting, as already you know the topic, that it is the art and challenges. So what will be the possible art while we will try to design a printed antenna arrays, or what might be the possible challenges or precautions we have to take in care while designing the printed antenna arrays, and how those shortcomings or challenges we can overcome. What might be the future of antenna array? We all know that 5G is about to deploy it. So antenna array definitely, or MIMO structures will definitely will play a vital role in that. So that's why I have selected, or I have invited today's speaker, Dr. Abdel Latif Slami. He is from Morocco, a very good friend of mine, and he is an expert in antenna array. He has many works, he has carried out many publications specifically focused on antenna array. He has other number of publications also on different topics like the important RF microwave components or different concern on ultra wideband antenna like that. But he is an expert in antenna array. Apart from designing antenna array, he works with the optimization techniques or optimization algorithm of antenna array. So hopefully it will be a very nice session. And already, as our coordinator introduced, that he is presently engaged in intelligent system, geo resources, and renewable energies laboratory at University of Sidi Mohammed bin Abdullah, Faculty of Sciences and Techniques, that is in Fez, Morocco. And at present, Dr. Islami's research areas include numerical methods, array antenna, radar systems, ultra wideband communication system, RFID systems, uh, which are for microwave applications. So hopefully it will be a nice session, and I will request to each and every participants that obviously I know that you all will cooperate with us, and as it was instructed that please do not turn the mic of speaker off because it will create interruption for the active participants. So now I will not take any more time. Already it's 6:10 minutes past. So now I welcome Dr. Selami on behalf of IMPS Engineering College. Sir, please carry out the session today.
Hi everyone. So firstly, let me to thank every person that associated to elaborate and organize this conference, this webinar. I will to thank Dr. Das for his invitation to be an international speaker in this webinar. I will thank every person that associate from the near or the far to organize this conference webinar. So today I will talk about branch arrays antennas. I will share my screen with you. Okay. So I will talk about branched antenna arrays. What does mean an antenna array? Why we use antenna arrays? What different geometry does we can find in antenna arrays? What the problematic that we can face when we conceive an antenna array? Okay, so I will talk about the arts and challenges in designing branched antenna arrays. So the plan that we use for this presentation, I will begin by small bibliography background, academic background. So arts of antenna arrays, problematic design, challenges design. Okay. So about my academic background, I have PhD in telecommunications and electronics from Sidi Mohammed bin Abdullah University, Faculty of Science and Technology, Fez in Morocco. Okay, so I have a master degrees in telecommunication and microwave devices from Sidi Mohammed bin Abdullah University National School of Applied Science, Fez, Morocco. So about my research area, I work in numerical method, arrays antennas, radar systems, ultra-wideband communication system, RFID systems, and microwave applications. So about my research work carried out in collaboration with other people. So I have 15 journal papers indexed in Thomson Reuters copies, Web of Science. I have 21 international conference paper. So the art of antenna arrays. So what does mean antenna array? So an array antenna is a set of multiple connected antennas, single antennas, which work together to transmit or receive radio waves. Okay, so in array antenna, several single antennas separated from each other are geometrically arranged to give desired radiation characteristics that are not possible to achieve with a single antenna. Okay, so the question that we can put, why we use these array antennas? Why we use an array antenna instead of a single antenna? So we have two cases. The first case, when we talk about high radiation performance, okay, high radiation performance. So high radiation performance, and the second case, when we talk about smart beam steering. Okay, high radiation performance, for example, I have antenna with a single antenna with 1 decibel, but my application needs 20 decibel. So I talk about high radiation performance. I need array antenna to achieve to satisfy my application. And the second case, when talk about smart beam steering. Okay, directed my beam toward desired direction. So the question, how we can differentiate between these two cases? Okay, so the first case, so if we have multiple antennas connected to a single part of excitation, multiple antennas connected to a single part of excitation, so here we can talk about high radiation performance. I improve my radiation performance of antennas. Okay, so for example, we have these two figures. The first figure one, linear array antennas. So I have a single port of excitation with a serial distribution of radiating elements. So here I can talk about high radiation performance of this array antenna. The second figure is a planar array antennas. Okay, I have a single port of excitation used to power all antenna elements. Okay, so here the second case. So we talk about improvement of radiation performance of our antennas. Okay, so I take this example. Okay, so figure 3A, we have a single antennas with 3 decibel in directivity. Okay, so these antennas that covers our area for example, this application of planes or aircrafts. Okay, so this antenna does not covers this area. So what I need to do? I need to work by not plan, but an array antennas. Okay, so for example, in figure B, we have array antennas with 6 elements, 1, 2, 3, 4, 5, 6. Okay, so these array antennas have a directivity of 18 decibel. Okay, so we can say that our antenna, it covers the area of our airplane. Okay, so this is the difference when I use a single antenna and array antenna with a single part of excitation, just one part of excitation. I improve my radiation performance. Okay, so this is the first case. So we have other parameters. Sorry, something happened.
No, you carry out. No problem.
Yes? Some problem here.
Please share your screen once more.
Okay, okay. It's okay. So, I talk about array antennas with single parts of excitation. So we use it just for improvement of radiation performance. So we can talk about other parameters is half power beam width in array antennas. Okay, half power beam width. So each antennas have a half power beam width parameters. This parameter we use it to know how is the antennas or the array antennas is directive, more directive or small directive. Okay, so each antennas each array antennas have these parameters. So how we can determine these parameters? So we take the principal beam of our array antennas in red color. For example, here we have principal beam in red color, and we have secondary lobes or side lobes in blue color. So the principal beam, we take the maximum of radiation, and in decibel, we decrease by 3 decibel. So the intersection of our beam with the 3 decibel can determine the half power beam width. So this angle is in degrees, okay? So we can now do half power beam width in our array antenna. So each array antenna, more the half power beam width is small, more the antenna or the array antenna is directive. Okay, more the half power beam width, this parameter is small, more our array antennas is directive. So we use this parameter to know how much our array antenna is directive. Okay, so we pass for the second case, the beam steering. So if we have more than one port, okay, of excitation used to power multiple antennas, so here we talk about smart beam steering. Okay, we have a lot of ports used to power multiple antennas. For example, here we take this example. We have figure 4 hybrid coupler with 2 inputs and 2 outputs, and we have figure 5, we have a Butler matrix, just an example of matrix. So we have 4 inputs, 1 2 3 4, and we have 4 outputs, and these 4 outputs are connected to a microstrip antennas, rectangular microstrip antenna. Okay, so we have 4 inputs, 4 outputs. This Butler matrix is composed of several hybrid coupler. This hybrid coupler that we have in figure 4 is used to conceive our Butler matrix here. So 1 2 3 4 5 6 7 8 8 Butler matrix are used to conceive our each hybrid coupler are used to conceive our Butler matrix. So this is an example of 4 multiply 4 of Butler matrix. We have other examples, for example, 8 inputs and 8 outputs, 16 inputs, 16 outputs. Okay, so we have a lot of inputs and input ports for power, and we have a lot of output. Okay, so in this example, we take this example. So for Butler matrix of 4 inputs, we have 1 2 3 4 inputs. So if I exceed, I power the first part of the first input. Okay, the first input, I have a radiation pattern or main beam toward direction 1. Okay, if I power the second direction, I have a beam toward direction 2, and 3 toward direction 3, and 4 toward direction 4. So if I power the fourth input, I have fourth beam in output. Okay, so here we don't have principal beam and secondary lobes, but we have four lobes. Okay, four principal lobes. Each lobe is directed toward a direction, a precise or desired direction. Okay, so here I talk about Butler matrix for as beam steering. Okay, so we have four inputs and we have four outputs. The four outputs are connected to four antenna elements. Okay, this is the second case. So now I will talk about antenna array geometries and feeding techniques. Okay, the feeding. We talk about serial feeding and parallel feeding. What the difference between serial feeding and parallel feeding in arrays antennas? So this example for linear patch array antennas. So figure 7, we have serial feeding. We have one port and we have one feed line, one single feed line used to power all antenna elements. Okay, but figure 8, we have parallel feeding, so each antenna has a single feed line. Okay, each antenna. So the difference between these two techniques of feeding. So for serial feeding, figure 7, for serial feeding, okay, if I change frequency, input frequency, for example, I work with 2.4 gigahertz and I change the input frequency for 3 gigahertz. So here, the phase shift between antennas elements change. Okay, change. The phase shift between antenna elements change. We have one feed line, and when I change the frequency, the phase shifts also change. Okay, this is the problem in serial feeding. But for parallel feeding, when I change frequency, I cannot say a changement in phase shifts between antennas. Why? Because each antenna have the same distance between input of antenna and output of we have the same distance between the port of excitation and input of antenna. The distance between input of antenna and port of excitation is the same for all antennas. So when I change frequency, the phase shift doesn't change between antennas. Okay. This is the difference between serial feeding and parallel feeding. When I change frequency for serial feeding, the phase shifts change, but for parallel feeding does not change. So we have here planar patch array antennas. Okay, so figure 9, we have serial feeding. We use just one single feed line to power all antenna elements. Okay, one feed line. So here this is the same. When I change frequency, input frequency, the phase shift change between antennas. So figure 10, we have parallel feeding. Okay, so each antenna has the same distance between its input and the parts of excitation. Okay, for parallel feeding. When I change here frequency, I don't have any change in phase shift between antennas. So the last geometry, we talk about circular patch array antennas. Okay, so figure 11, we have serial feeding. So each antenna is connected to other antennas. Okay, and we have input excitation. Okay, the port of excitation in yellow color here. For the figure 12, parallel feeding. Okay, so we have the excitation in the center of array antennas. Okay, so the distance between the input power and the antenna is the same for each antenna. Okay, so this is the difference between parallel and serial feeding in arrays antennas. So, problematic design. So, when we need to conceive an array antennas, what the problematic that we can face in this case? Okay, so in general, we have one problematic. The problematic of secondary lobes and the mutual coupling between radiation elements. Okay, we talk about side lobes and mutual coupling between radiation elements. So here, we have secondary lobes, and you know the effects of secondary lobes. Okay, secondary lobes, you know the effects of them. It's produce interference with other signals, okay, and overlapping of our signal, and mutual coupling, it decreases the radiation performance of our array antenna. So we have a mutual coupling between this element and this element. So to understand that, so we take the first case. When so here, where when I increase the distance inter elements between two antennas, I increase the distance inter elements. Okay, I increase the distance between the radiating elements. So what's happened here? The mutual coupling between a radiation element decrease. Okay, when I increase the distance inter elements between these two antennas, for example, the mutual coupling decrease. So it's an advantage for us, decreasing of mutual coupling, but the problem that secondary lobes increase, it's an inconvenience. Okay, secondary lobes increase. The number of secondary lobes increase when I increase the distance inter elements between two antennas. Okay, so this is a problem. So if we take the other case, I decrease the distance inter elements between two antennas. Okay, what's happened here? So if I decrease the distance inter elements, I can say that the secondary lobes, side lobes decrease. So it's an advantage for us decreasing of secondary lobes, but the problem in terms of mutual coupling. Mutual coupling increase. If mutual coupling increase, the problem of decrease of radiation performance, we can affront it. Okay, faces it. So what is the solution? Okay, what we can do for this problem? If I increase the distance inter elements, the mutual coupling decrease and secondary lobes increase. But if I decrease the inter element distance, the secondary lobes decrease and the mutual coupling increase. So in every time we have a problem. So what we can do? So for us, we are studying the distance inter element between these two antennas. Okay, so we choose the best inter element distance that can give us high radiation performance with the minimum secondary lobes, and after we search a manner to decreasing the mutual coupling between radiation elements. Okay, so for the first case, we take a linear array antennas in figure 16. So we have a linear array antennas. Okay, this is so the total file radiated file by these array antennas equal the superposition of all elements, radiating elements of antennas. Okay, so we assume that our array antenna is isotropic. That means that each antenna is the same to other. Okay, each antenna is the same to other antennas. Okay, so the total far file radiated by this array antennas is equal to the summation of all radiating single antenna. Okay, so after some calculus, we can find that the total file equal a reference multiplied by array factor. So a reference, we can assume that array the file the radiation, but the single antenna at origin, okay, at origin of our repair is the reference. Array factor, we can see that depends of number of elements of antennas, and is the number of antennas, and X. So X, if you look, it depends of K. So K is the wave number K. D is the distance inter element, distance between two antennas. Okay, D. Theta is the angle between the Z axis and the point in far phi, the point M, which we do to calculate. Okay, so the distance, the angle between the Z axis and the point M in the far phi, it's the angle theta. Okay, so phi is the phase shift between two successive antennas. Okay, phase shift is the phase between two successive antennas. Okay, so array factors, it depends on distance inter elements and phase shift. It's the same for a planar array antennas. Okay, we work with the same manner. So here we can find that the total file equal a reference. C'est-à-dire, that means the far file at the center origin. Okay, multiplied by array factor in X direction, okay, and Y direction. Okay, so a total equal a reference multiplied by array factor, and array factor depends on two parameters. So parameters along this, the x-axis. So we have M, it's the number of antennas along the x-axis, and N is the number of antennas along y-axis. Okay, so Sx and Sy, it depends also by the number wave and distance inter element between two antennas, dx between two antennas in x direction. So theta is the angle between z axis and point in far phi, point M. Phi is the angle between the x axis, okay, x axis, and the projection of point M in the plane x or y. So okay, this angle phi. And gamma x is the phase shift between two antenna elements in x direction. Okay, phase shifts between two antennas in x direction. It's the same for Sy. We have k, d is the distance between two antennas in y direction. Theta and phi is the angle is the same, and gamma x is the phase shift between two antennas in y direction. Okay. For circular array antennas, so we have the total file equal the file of an origin, okay, multiplied by exponentially xn. So xn, it depends on the number of y. Q, R is the radius of our array antennas. So here we don't talk about distance inter element, but we talk about radius of array antennas. Okay, a linear and planar, we talk about inter element distance, but in circular array we talk about radius parameters. Okay, so we have beta and beta n. Beta is the angle between the x-axis and the projection of points M in plane X or Y. Beta A is the angle between the x-axis and the antenna number A. Okay, and phi n is the phase shift between two antennas. Phase shift excitation between two antennas. Okay. So array factor is depends in this parameter Cn, and Pn equal this equation. So we will present the directivity of each array antenna. So the directivity, the definition of directivity equal the maximum radiation Emax per the radiation intensity in the desired direction. Okay, the maximum radiation intensity per the radiation intensity toward the desired direction. So we can assume that the maximum radiation intensity is equal to 1, okay, and we can determine the radiated power by equation 10. Okay, it depends of array factor. Okay, this is our array factors of each antenna. Of each array antennas, we have a power or radiated power. So we can replace it, the array factor of, for example, linear or planar or circular array antennas, and we can find the radiated power. And if we find the radiated power, we can find the directivity of array antenna. So you can see that array factor, that directivity, it depends of array factor, and array factor depends of distance inter element and phase shift. Okay. So in the next, we will present MATLAB simulation results. Okay. So we studied the inter element distance and effect of phase shift in several arrays antennas. Okay. The distance inter element and phase shift excitation, what their effects in arrays antennas. So the first case, we have directivity of linear patch array antennas of 6 elements. Okay, we have 6 elements of our linear array antenna. So we have directivity in decibel, and x-axis we have the direction of propagation. So for our example, we choose that direction of maximal radiation is toward the angle 90 degrees. Okay, 90 degrees. This is the direction of maximal radiation. So if we take the first inter element distance, d equal lambda per 4, so the black color, we can say that we have one single beam, principal beam, okay, and 2 secondary lobes for the first inter element distance. Okay, it's the small distance here. If we increase for d equal lambda per 3, okay, lambda per 3, we can observe that the level of radiation performance increase in comparison with the last case. Okay, the level of radiation increase. The half power beam width increase also in comparison with the first case. Okay, so if we pass for d equal lambda per 2 in red color, also the level of radiation increase in comparison by the two case. Okay, in red color we have one beam. Also the half power beam width, the width of our beam decrease in comparison with two case. Okay, and the number of secondary lobes increase also. Okay, so if we increase the distance inter element, we can observe that the radiation performance increase, the level of radiation increase, and also the secondary lobes increase. So for this distance d equal lambda per 2, we have one principal beam and two secondary lobes in the left and two secondary lobes in the right. Okay, so we have increasing the secondary lobes. If we go to d equal 3 per 4 lambda in blue color, so we can observe that the radiation performance, the level of radiation increase also in comparison by this 3 case. But the problem in terms of secondary lobes, we have 4 secondary lobes in the right and 4 secondary lobes in the left. Okay, so more the distance inter elements increase, more the level of radiation increase, but the problem of secondary lobes also increase. So here we have started the effects of inter element distance. So we go to phase shifts. Okay, phase shifts. So here we have the effect of phase shift excitation in our array antenna 6.1. Okay, so directivity of linear patch array antenna always 6.n. So the phase shift. So the first case, we have the phase shift equal 0. So the direction of propagation, the direction of maximal propagation is toward always 90 degrees. Okay, so in blue color, we have the radiation performance of our principal beam toward this direction. Okay, so if we change the phase shift to P par 4, okay, what's happened here? We can observe that just the direction of propagation that change, okay, change toward this angle 110, I think 110 degrees about, okay, but the level of radiation stays stable. We don't have any effect on level of radiation or in the beam width. Okay, so the phase shift. So if we go for P equal P per 3, also the direction of propagation change and the level of radiation stay stable. Okay, so the phase shift just affects the direction of propagation, and this technique that we use for beam steering. So we can talk about intelligent arrays antennas. We change just phase shifts, and we can direct our radiation toward the desired direction without touched the array antennas. Okay, just change the phase shifts, and we can direct our radiation toward the desired direction. Okay. So if we pass for planar array antennas, so directivity of planar patch array antennas 6.6. Okay, it's a planar array antenna. So here we have two distance antenna elements, distance toward X direction and a distance toward Y direction. Okay, so for our example here, we have two direction of propagation of maximal propagation. Okay, so we take just the first case, the propagation toward 0 degrees. Okay, we talk about 0 degrees toward 90 degrees. Okay, 0 toward 90 degrees. So here, if we take the first case, dx equal dy equal lambda per 4, so black color. So in theta equal 0 degrees, okay, so we have one single beam. This is one single beam with one secondary lobes, okay, one side lobes. For the first case, the x equal dy equal lambda per 4. Okay, so if we increase the distance toward lambda per 3, the second case in red color, what happened? We can observe also that the level of radiation performance increase. Okay, the half power beam width decrease. Okay, so directivity increase, so the half power beam width decrease. Okay, and we can observe that the number of secondary lobes go to increasing. Okay, secondary lobes. So for the third case, the x equal the y equal lambda per 2. So what's happened here? So here in pink color. Okay, so here, so the level of radiation increase in comparison with the two cases. Okay, so the level of radiation increase also. Okay, and the half power beam width decrease, and the secondary lobes, number of secondary lobes increase also. Okay, and the last case, we have the x equal the y equal 3 lambda per 4 in blue color. So we have the high level in this case, and in the number of secondary lobes, we have 4 secondary lobes. Okay, so in planar array antenna also, when we increase the inter-element distance between two antennas, so the level of radiation increase, but the secondary lobes also increase. So we go to directivity of circular patch array antennas. Okay, directivity of circular patch array antennas of 6 elements. Okay, so here we talk about radius, not distance antenna elements, but the distance, but the radius of our circular array. So the first case in pink color R equal lambda per 4. So we can talk about omnidirectional array antennas. Okay, this lab we can assume is like omnidirectional array antennas. Okay, so if we go to R equal lambda per 3, what happened here? We can observe that the level of radiation increase, okay, in angle theta equal 0 or theta equal 180, okay. So the level of radiation increase. If we go to R equal lambda per 2 and red color, okay, what happened? We have the maximum radiation in this distance anter element. Okay, the maximum the radiation. So we have one beam, okay, one beam and one secondary lobes. If we go toward R equal 3 per 4 lambda, so here we have level. So the level of this case decrease in comparison by R equal lambda per 2. Okay, it's the same for R equal lambda in green color. So in this array antenna, circular array antenna, the high radiation performance, we can find it at R equal lambda per 2. Okay, so the best inter element distance for high radiation performance in circular arrays is lambda per 2. Okay, so the effect of phase shift in this array. So we have studied the phase shift, the effect of phase shifts in these circular array antennas. Okay, so the first case in pink color, phi equal 0. So the maximum radiation is toward this direction, theta equal 0 and theta equal 180 degrees. So if we change the phase shift, we can observe that we have any change, no effects in radiation performance. So for this type of circular antennas, when we change the phase shifts, we have no effects on radiation direction like or linear array antennas. Okay, so for circular array antennas, we change phase shifts, but the direction of propagation does not change. So if we take conclusion of this simulation MATLAB, so we have linear array antennas, planar array antennas, circular array antennas, and we have distance anter elements between each elements of antennas. We have J, it's the gain of our array antennas. D is the directivity of our array antennas. Half power beamwidth in degrees of each antennas and each case, also for the planar and circular. So if we take the values of each array antennas, so from this study and other studies that the researchers make, we can conclude that the best inter element distance that we can use for array antennas is lambda per 2. This is the desired, I don't say desired, but this is the best inter element distance fixed by all researchers. Okay, in this distance we have a high level performance and minimum secondary lobes in comparison with other case. Okay, so lambda per 2 is the best inter element we can use for array antennas. Okay, so now we got to talk about mutual coupling, okay, between a radiation element. So if we fix inter element distance at lambda per 2 for our array antennas, so we have other methods to decreasing to resolve the problem of mutual coupling. Okay, so here we have three methods, three manners to decrease the mutual coupling between radiation elements. The first, we can talk about OBG structures. Okay, we can talk about OBG structures, electromagnetic band gap. Okay, the second method is defected ground planes, DGS. Okay, and the third case is split ring resonator, SRR. Okay, we have three methods used to decreasing mutual coupling between radiating elements in each type of arrays antennas. Okay, so if we talk about OBG circuit, the first case. So for this case, we have three types. We can talk about OBG structures, one-dimensional and two-dimensional and three-dimensional. So these OBG structures in general, OBG structures are defined as periodic or no periodic artificial structures, okay, OBG structures, so which prevents the propagation of electromagnetic waves in specific frequency band, okay, for all angles of incidence and all polarization states. Okay, so the role of these OBG is just to prevent the propagation of electromagnetic waves between two antennas in a specific frequency band. We can assume that like filters. Okay, we can put between antennas just like filters. Okay, so we have here one-dimensional OBG structures like holes in ground plane. Okay, like holes. The second case, we have OBG structure 2D, okay, two-dimensional. So like here, the structure mushroom-like, okay. We have over here between radiation elements and ground plane, okay. Between radiation elements and ground plane, we have over here. It's like a mushroom, okay. And the third case is 3D OBG structures. Okay, so these structures would figure A would pair structures consisting of square dielectric bars. Okay, and B is a metallic tripod multi-layer network. So this we can find in all substrates. Okay, in all the substrates of our array antennas. So one dimension just in ground plane, two-dimension just two-dimension in the substrate, but three-dimension we can find the structure in all substrates of our array antennas. So if we talk about the second case, we can talk about defected ground planes, DGS. So here we can make several slots in ground plane. So this technique is used in ground planes of our array antennas. So the first case slot in between two antenna elements in the ground plane. B, meander line, okay, under our radiating elements. Figure C, different slots under our array antennas and ground plane, and figure D, different form of dumbbells in the ground plane. Okay, so this technique is used in ground plane, defected ground plane, just in terms of ground plane. The last case we talk about split ring resonator, SRR. Okay, so here we talk about artificial structures. Okay, so in the nature, the material is we can talk about a material that have a permittivity and permeability positive. Okay, in the nature we don't have permittivity negative or permeability negative. Okay, so if we talk about the trihedron KOH, okay, I talk about this. So we have the direction of propagation K equal A vectorial B or H. Okay, just this is the trihedron of electromagnetic transmission. So A It depends on permittivity, okay, and H or B depends on permeability. So if permittivity and permeability has the same signs, positive, positive. So K is positive. We have the transmission of signals. Okay, we have transmission of signals in our array antennas. If we talk about on negative permittivity and negative permeability, okay, so also negative vectorial negative give us a positive number wave. So we have the transmission, okay. But if we talk about two sign different, okay, two sign different, for example, permittivity is negative and permeability is positive, or permittivity is positive and permeability is negative. So here, if we put this structure with this characteristic in our array antennas, okay, so here we cannot have transmission between these two antennas, okay, because the K number is opposite of our direction of propagation, okay. This is the technique used in split ring resonator. This is on artificial magnetic materials, okay, artificial magnetic materials. So we conceive materials with opposite sign to stop transmission between two antennas, okay. So this is several forms of split ring resonator. So figure A, we have rectangular SRR, rectangular, and B, modified SRR, MSRR. Say resonator with three spiral tunes. So we have the first spiral, the second, and the third spiral, and they Hilbert fractal curves. So we can use this technique, the last technique, in fractal arrays antennas. Okay, so this is we have an example of antennas. Okay, monopole antennas. We have the first and the second antennas, and I have an example of SRR resonator. Okay, spring resonator. Okay, SRR structures used in this array. In the literature, I don't work in this technique, but I find it in literature. Some people work with this technique. Okay, so for us, we are working with OBJ structures. Okay, we made some simulation for OBJ structures. Okay, so our structures like that. So it's a periodical circular structures is composed of several circular structures. Okay, so we can find the relation between impedance and resistivity. Okay, impedance and resistivity. So our idea here, what is our idea? We need to conceive an OBJ structure that have a high resistivity, okay, high resistivity to stop the passage of electromagnetic waves between antennas. So we search for a material that have a high resistivity. And we have the relation between impedance, so impedance Z equal R, because we talk a real impedance, because our source, our power used have 50 ohm. Okay, impedance, input impedance of our source equal Zn equal 50 ohm. Okay, for that we choose Z of our structure equal R equal 50 ohm. Okay, so we have the relation between impedance and length of our structure and surface of our structure. So if we have these three parameters, we can conclude the resistivity of our OBJ structure. Okay, so we have here resistive materials and cut phase. So this is the proposed OBJ structure. So we can put this structure in our array antennas. So we have here figure A and B. Figure A, we have our array antennas without any structure, and figure B, the structure after Okay, we have the array antennas with our structures. So figure 31, we have the transmission parameters between two input ports. Okay, two input ports. So if we look, when we put OBJ structures, we can find that the transmission decrease between antennas. Okay. Also, if we talk about the matching S11 parameters, so if we add OBJ structures, we can find that the level of radiation, the level of matching is improving. Okay, so when we put two structures, the level of matching improve, and the transmission between horizon antennas decrease. So if we talk about surface file distribution, so the first case, so figure 33, okay, 33, we have a file before OBJ structures, so the level of the maximum level of a file is equal 70.577 volts per millimeter. Okay, so if we pass toward the second case, when we have a file after OBJ, so we can find that the level of radiation increase, okay, toward 25.786 volts per millimeter, with a difference of 8, okay, 8.29 volts per millimeter. So we can observe that when we put OBJ structure, the electromagnetic electric file, radiated file or surface file increase. The second case, we have a planar array antennas. Okay, so we have two ports here, and we have a ground plane, a partial ground plane. So these array antennas, the first linear array antenna and this array antenna, are array antennas used to ultra wideband communication. We have worked with these array antennas for ultra wideband communication. For that, we have partial ground plane. This technique is used to have ultra wideband characteristic. Okay, so for this geometry, we have S12 and S11. Okay, so for transmission between antennas, figure 36, we can observe that the transmission decrease when we put OBJ structures, and also for S11, so the matching, we can observe that we have improved our arrays, our matching. So our array antenna work for the band 4 to 8 gigahertz. Okay, our array antenna work in C band. Okay, C band. This array antenna used for C band application, ultra wideband communications. So the same for surface A file distribution. So for the first case, figure 38 of file before OBJ, so the maximum radiation or the maximum of file distribution equal 60.88 volt per millimeter. So if we pass for the second, when we have a file after OBJ, so we can find that we have improved our radiation toward 21.72 volts per millimeter. Okay, with a difference of 4.36 volts per millimeter. Okay, so we can observe that when we put OBJ structures, the transmission between antennas decrease, and the matching improve, and the surface wave file improve. Okay, so the last axis we talk about challenge design. Okay, so for challenge design, we can talk about compact and low profile. So for horizon antennas, we search to decrease the dimension, miniaturize our horizon antennas. If we have a miniaturized array antennas, it's well for us. Okay, it's good for our application. So we can talk about compact and low profile, and high radiation performance. Okay, so we talk about miniaturization and high radiation performance. Okay, high radiation performance, high directivity, and high gain and high efficiency. Okay, we talk about low material coupling also. Okay, so high radiation performance and low material coupling. We search to decrease the material coupling between radiation elements. We talk also about the flexibility of our array antennas. We can put it in each circuit, in each equipment. Okay. We talk about configuration and orientation. Configuration, we talk about frequency. If I have array antennas that can function for several frequencies,
Professor, please unmute your mic. Someone has muted your mic. Please unmute your mic. Professor Srimani, please unmute your mic.
now it's good.
Yes, it's good, ma'am. Yes, yes.
Okay, so I talk about compact and low profile. I talk about high radiation performance. So we search array antennas with high radiation performance and low profile. That means miniaturized. We talk about low material coupling. We search the low material coupling between radiation elements. We talk about flexibility. If we have array antenna that we can put it in each equipment, it's good for us than other antennas that have big dimensions. Okay, we talk about configuration and orientations. So configuration, we talk about array antennas that can work for several frequency. Okay, several frequency configuration. We talk about configuration. If we have array antenna that work for several frequency, it's better than antenna that work for one single frequency. If we talk about orientation, or we talk about beam steering, intelligent beam steering, we can toward our direction of propagation toward any direction. Okay, so multi-mode operation, we talk about mode TA and mode TM. Okay, and multiple frequency bands. So if we have array antennas that work, for example, for wideband and ultra wideband and 5G is better. Okay, so we talk about multiple frequency band. This is some challenges design in arrays antennas. So I finish. So if you need to contact me, this is my Abdel Latif, IB point Slimani arobas UCMBI.ac.ma. Okay, MA. Our YouTube channel with some colleagues is this is our channel in YouTube. Okay, Safi Lalet for engineering. We put some videos for antennas, and we will put other videos, and we put some videos for network also, and we will work for anything that have relation with telecommunications area. Okay, so thank you for your attention, and if you have any question.
So dear participants, if you have any questions, you may write in the chat box now.
Okay. About how we can How we can how we can achieve S-band using antenna array. So S-band, we choose the high frequency in our band, okay? We choose the high frequency of our band. For example, if we talk about C-band, we have the high frequency is 8 gigahertz. Okay, so we can calculate the dimension of our horizon antennas at 8 gigahertz. Okay, so you know that more the frequency increase, more the dimensions of our horizon antennas decrease. Okay, so if we work with 8 gigahertz, it's better than work with 4 gigahertz. For 4 gigahertz, we can find array antennas with high dimensions, but for 8 gigahertz, we can find small array antennas. Okay, so I talk about dimensions of array antenna. It's the same for S-band. Other questions? So how we can overcome the challenges of the design. So for example, if we talk about high radiation performance, the number of elements of array antennas increase, more the directivity increase. Okay, more number of antennas increase in our array, more the gain and directivity increase. But the problem of mutual coupling, I see three manner to decrease the low mutual coupling. Okay, and for others, just we can work at the structure of our array antennas, for example, for ultra wideband communication or wideband, we work in ground prior, for example, or on multi-couche, multi-layer antennas to have ultra wideband communication or wideband band. Okay. So what is difference between MIMO and array antenna? So MIMO, we talk about multiple inputs and multiple outputs. It's like Butler matrix Butler. Okay, if we go toward Butler matrix is an example of MIMO application. Okay, each direction we have a radiation performance or log toward a direction. Okay, so in this direction we can receive a signal, and this direction we can receive other signals and other. Okay, so here we talk about MIMO application. But if we talk about array antenna, so array antenna, we can talk about array antenna in general. MIMO Butler matrix is array antennas also. Okay, array antenna. But your question, what do you mean by array antenna? With one single beam? Okay, array antenna. Do you mean by array antenna that have one single beam? So I see the difference between MIMO and single antenna. So for example, for these antennas, we have one single beam with secondary lobes. So one single beam toward our direction, desired direction. But for MIMO antennas, we have several direction of propagation. We don't talk about secondary lobes, but we talk about several beam steering. Okay. It was shown around 25 watt per millimeter. Please give feedback link. I am designing antenna in micro dimension. Then what are dominating parameters? I am designing antenna in micro dimensions. What are dominating? I don't understand I am designing antenna in micro dimensions. So we have parameters of any antennas. We have the width and the line. So if we work, so for each antennas, we have three parameters. We have frequency, and we have permittivity, and we have thickness of the substrate. So from these three parameters, we can conceive our antennas. Our antenna depends on W and L, width and length. Okay. So about dimensions of horizon antennas and dimensions of feed lines. Okay, so I put, or we put in our channel YouTube, we put the technique used to find the dimensions of rectangular and circular patch antennas, and also the dimension of feed lines. Okay, if you search in YouTube channel, you can find two videos, one for dimensions of rectangular array antenna and its dimensions of feed line, also for circular patch antennas. Okay, so what is condition of OBG when we simulate this in CST or minimize the mutual coupling? So the condition in terms of impedance, and we talk about impedance of our OBG structure. Okay, so here, so we have impedance of our structures, and from impedance and dimensions we can determine the resistivity, and if we have the resistivity we can determine the nature of our uh, our structure. Okay, parameters, permittivity and permeability. If we have resistivity, we can know what the type of this structure. Okay, so we have impedance and we have dimensions. We can determine the resistivity, and for that we can know what type of this structure. So I need to design SRR with microstrip. How to do, which software is best? So for us, we work with HFSS and CST. These two software, I think, are fiable in microwave antennas or microwave structure in general. How to make design of radiation pattern antenna to become more directive? So, if we talk about directivity, more the number of antennas in array increase. For example, if we have array antennas with 6 elements, is better than antenna of 2 elements. More the number of antennas increase, more the directivity increase. Okay. So for directivity, we talk about the numbers of elements. Also, we can talk about the nature of substrates. Okay, if I work with Roger, is better for than epoxy, for example. FR for epoxy, Roger has high characteristic in terms of directivity and gain in comparison with FR for epoxy. Okay, so what is the difference between natural OBG and artificial OBG? Natural OBG. So in terms of parameters, okay, for us we need, for example, we don't talk about OBG, but for natural and artificial, I go to SRR here. So each parameters, each case, so for this case, we have natural materials, permittivity is positive and permeability is positive, but for artificial materials, we have different sign. Okay, so what we need, if we need double negative materials, so we need to conceive materials with negative parameters. Okay, so what do you need for you? What's application? In figure 90, is the increase in the number of lobes really problematic, because more side lobes actually should decrease the side lobe power as the total area under the curve is decreasing. Please follow if I have. So figure 90. I go to figure 90. Yes. So here. So here, if we talk about inter-element distance. So for the first case, D equal lambda per 4. So if you do not need the high level of radiation, if you need just, for example, here, if we have 10 decibel, if you need just 10 decibel in your application, so you can work with this inter-element distance. So here we have 2 secondary lobes. Okay. If you need more directivity, so you need to increase the inter-element distance. Okay. For example, for D equal lambda per 3, the level of radiation increase. So I talk about 6 elements. I have, for example, in our laboratory, just 6 antennas, array antennas with 6 elements. Okay. Array antennas with 6 elements. So to
Professor Julami, please unmute your mic.
Okay.
Yeah, that's good.
So I see it depends on your application. If you need high radiation performance and you have just array antennas with 6 elements, so you need to increase inter-element distance. And you know, if we increase inter-element distance, the secondary lobes also increase. But if we have 2 secondary lobes, it's better than 4 secondary lobes and better of 6 secondary lobes. Okay, we search case the main case. Okay, I wish that you understand me. For other question, you can contact me in my mind. See, yes, I am working on a reflect array. Yes, I have required learning how to use formula of progressive fast shapes given in literature paper to duplication among files. If you help me in this regard, I will be thankful to you. So for this question, Sanya Tarek, okay, you have my mail and you can send me the detail of your work. Okay, what do you need, and we can discuss us. Okay, for reflector array antennas. I have one question. You have talking about distance between antenna elements and their effects on mutual coupling and secondary lobes. Yes. What about the length of the feed of antenna? Is there any condition about the dimension of the feed and their effects on antenna performance at high frequencies, especially mutual coupling? So if we talk about the dimensions of the feed line, so for feed line, if the feed line has big dimensions, so we have problem of radiation. Okay, so to avoid the problem of radiation, we need to decrease the dimensions of feed line. Okay, we need to decrease the dimensions of feed line to have array antenna. We can talk about just radiation of radiating elements. Okay, so if the feed line has big dimensions, so it's radiation, and if the feed line radiation, so we have a problem of mutual coupling. We need just radiating element that radiates. Okay, just radiating element that will radiate. And feed line, if has big dimensions, it radiates also. It's a problem. We need to decrease the feed line dimension. So I repeat, the feed line dimensions, I put a video in YouTube that talk about the feed line dimensions. So just 1 minute here. So this channel, we have this channel with other persons, other colleagues. So here,
Dr. Slami, please unmute your mic.
okay. So in this video, we talk about dimensions of rectangular patch antennas and its feed lines dimensions. Okay. Circular, okay. So in this video, other video, we can talk about circular patch antenna dimensions and its feed lines dimensions. Okay. So we have two videos in this channel, and we talk about rectangular and circular patch antennas with its feed lines dimensions. How to get equivalent circuit. So for equivalent circuit, so here we can talk about we need another science for equivalent circuits of array antennas. We can talk about inductance and capacitance, okay, and the resistance. So we need other science for this question. If I am designing antenna in micro dimension, yes. Material. Which antenna structure is suitable for line imaging using ultrawideband? Which antenna structure is suitable for line imaging using ultrawideband antenna? I don't know what does mean. What do you mean by line imaging? Line imaging. Feedback from yes. How to simulate a perfect FPG to minimize the material coupling. So we have.
Okay, so Dr.
Yes.
Yes, already we have we have one 1 hour 30-minute session as per our discussion, and already you have addressed many questions by the participants. So
yes.
probably each and every questions can't be addressed now within the time limit. So can we end up the session now? If any participants have further query, they will contact us.
Okay.
Okay.
Okay.